Okay, now, as I said, I'm not saying the kind of reasoning emerging on this problem that I'm saying emerging in your homework. And I'm not sure that everybody's doing the homework by figuring out how to apply the principles. Okay. And I do see people doing some fairly good reasoning from basic principles in some cases here and on this quiz. But I don't, the reasoning I see isn't relevant to the situation. I mean, it is, but it's not going to help. Okay. So the first thing I do is analyze projectile. What do we know about the projectile? We've got the X motion and the Y motion. So I'll just say delta X, or I don't know if I want to do the function or an interval, but I'll do the function. Okay, so there's X of t. And what else do we know about the horizontal motion? Well, we could write down this equation of motion. But px equals p naught x. Okay. Well, let's see what we can get from the y motion. It might be more in the x motion, but the y motion is ay equals negative g. What else? And debating about how to write these equations out. I can write this much, and I can write more. I could write y squared equals y naught squared plus 2g, or 2 times the ay delta. Okay. But anyhow, we got the equations of motion here. And let's see if we got enough. What can we determine? What do we know about y? We know the acceleration. And we know the y displacement, right? Now another equation we could write is y of t equals I'm trying to remember how your book does it. I think they would use Vy bar delta t. So again, what do we know? We know that, I think it might be simpler now that I'm looking at this in terms of what I've seen. And I apologize for that, but we're looking at an interval here. So what we know is delta y equals -1 meter. Delta x equals 30 centimeters. And ay equals -g. Okay, I've got this in meters. I've got this in centimeters. Do we want to use meters in seconds or centimeters in seconds? The numbers are a little inconvenient either way. But I'm going to say delta x is 0.3 meters. So ay is -9.8 meters per second squared. That makes sense? What can we do from this? Again, in the y direction, we know that ay equals -g. And we know that delta y equals -1 meter. We also know that the initial y velocity is 0 because we get to assume that initially the thing is moving horizontally. I was going to start by listing equations that I think I'm just going to start by listing what we know. Okay, so delta x is 0.3 meters. A sub x is 0. So we know 2 things about the x motion. We know 3 things about the y motion. So I'd recommend setting up a projectile problem by listing what you know. For most projectile problems, you have enough information to figure out all the y quantities. We know how far it goes in the y direction. We know the acceleration. We know the initial velocity. Well, what can we find? We can find the time. Okay, so there are 2 equations we can use. We could use this one. That's a square. It turns out to be quadratic. And you have to use the quadratic formula generally to solve it if v naught y is not 0. But v naught y is 0. So we can get t directly from this. It's our solution. This term is 0. And we solve and we get the time. Okay, well, I've posted, I don't know if you've seen it, I've posted a bunch of questions that I want you to work out for lab, and that's due sometime Friday. Most of those questions can be answered. Most of the calculations can be done on a spreadsheet, and I want to see one sample calculation that shows you know how to analyze it. Okay? And one of the things you got to analyze is this situation, where you know this horizontal range, and you know the height. I measured a table last time, and I told you how high it was. I think about 97 centimeters if you're going up to the ramp. Okay. For do you know how to use cell references in Excel? Like you just put the height as 1 meter or 100 centimeters, whichever system you want to use. And then you do calculations referring back to that cell. So if you change the number in that cell, all your numbers change. Okay. So it'd be safe to use 1 meter if you can change that just with a couple of keystrokes and see what difference it makes. Doesn't make much difference. At 3 centimeters, it's pretty much doesn't amount to a hill of beans compared to the uncertainties in the other measurements. So you maybe can even stick with that, but you could always refine it by just changing that one cell. Okay. So what I'm going to say is, what I've said, I mean, I've told you, I'll go ahead and use Excel. I've also told you that you have to have a dedicated lab book, and I hope you do. If you don't get one, as it tells you to leave the first couple of pages blank. I'd leave the first 5 pages blank in case you want to put something in before this experiment. And do a heading and then leave 2 pages blank so you can fill in descriptions and stuff. I'm not going to ask for that on Friday. Just want calculations. And when you do graphs, I want you to do a sketch of the graph. It doesn't have to be a sketch that takes you 30 minutes. It's a sketch you can do in 2 to 3 minutes, where you at least label the important things in the graph. Okay. And if Excel gives you an equation, you write the equation. So you have it there in your lab book. You don't have to go to Excel to find it, but you always know where your Excel file is in case you got to change it or revise it. Does that make sense? So you want to follow the instructions I gave you because you want all this information in your lab book because we're going to use it throughout the semester. Okay. So follow the instructions I gave you. Okay, back to this. Okay, T's your time of fall. And this comes out about 0.44 seconds. It might be 0.45. Okay. And that's going to be the same when you're analyzing your lab for every fall, if you assume horizontal velocity. Okay, so you get the time of fall. Now, you can write out the equation of motion that you get by integrating constant acceleration twice. And that's the equation you get. You should always be able to write down that equation or derive it. And you could derive it from a V versus T trapezoid too. You should be able to do it both ways because it gives you 2 ways of thinking about it. Okay, so Okay, well, 0.3 meters over 0.44 seconds. I'm just gonna do ballpark approximation. You can use Excel and get it accurately enough. Excel might give you 10 significant figures, but 10 significant figures is ridiculous for the quality of data that you have. You have plus or minus a centimeter here and there. So 2 significant figures is probably going to be about all that's really, but to be safe, you can use 3. And you can put a note in your life, okay, I'm using 3 significant figures. It's too much, but just to be safe, 2 is probably right. I'm going to use 3. Does that make sense? And we'll talk about how you can determine the number of significant figures. Anyhow, we have this. There's your T. 0.7 centimeters per second. And I got a good night's sleep last night. I got no excuse. Put my V naught X and T in the wrong place. But the division is 0.3 meters divided by 0.44 seconds. It goes 0.3 meters, takes 0.44 seconds. So that comes out about 0.7 meters per second, not centimeters, it's meters. Write it out carefully like I'm not doing. Okay? Well, you can do that. It's a very short, simple calculation. You can easily do that by cell reference using Excel. You just put the delta X's down on the line and you do simple calculation. Then you can just drag it down and get all your velocities. Okay? Everybody know how to do that? If anybody does, let me know. I'm not sure how much Excel. I think you're using it. Some of your engineering classes and stuff. Okay, well, now what's the ball kinetic energy? And actually, I want you to write the kilograms and meters per second. And there we have it. I think those numbers are right. If you score 0.7, it's 0.49, which is about half. So you got half and a half is a quarter 0.06 is 0.015. So I think the numbers are right. So that's really easy, right? All you got to do is remember kinetic energy is 1/2 mv squared. Now I ask you about the ball's potential energy loss. What do you know about potential energy? I'm going to give you a chance to tell me if you do, if you remember it. We didn't do that much with it. So if you don't remember it, it's okay. I want to see if people do. Okay. Now, Potential energy change is equal and opposite to the work done by conservative forces. There are a few more words that ought to go around that, but that's the idea. And I want you to make it a point that that's the first thing you think of when you think of potential energy. You don't think of a formula. You don't think of MGH, because that's only the formula for gravitational potential energy near the surface of the Earth. If you're not near the surface of the Earth, it's maybe negative G, big M, little m over R. Okay? If it's an electrostatic force, it's a kind of an equivalent expression, except using K instead of G, and Q1 and Q2 instead of M, big M and little m. But you don't know what that means yet. It's always an integral. But near the surface of the Earth, the force is constant. Force on a given mass. So you can abbreviate that. Let's see if I can move this over a little bit. I need to anyway. I thought it was over far enough, but it wasn't. Okay. And let me give myself a little more room to squeeze myself into this corner so I get out of the way. Okay. Now, I haven't told you what a conservative force is. It's path independent. We need to have demonstrations and discussions and use that idea in lab week from Friday. Okay. But if the conservative force is gravity near the surface of the Earth, I'm going to say change of potential energy is mg, which is the force of gravity, times delta y, which is the displacement in the direction of gravity. And that's all I'm going to say about this, but for the purposes of looking at this experiment and getting an early handle on the energy, we're going to use that. And delta y is 5 centimeters. Okay, so that's 0.06 kilograms times 9.8 meters per second times negative 0.05 meters. Now that's going to give you 0.0003. So this is approximately equal to negative 0.03 joules. And you can work out the details of that. I mean, you want to write the units. I really want you to be using units throughout your calculations. I'm seeing errors, usually minor ones, because usually the solutions are pretty good. Okay. I'm just seeing a lot of numbers with no meaning. I'm not even seeing many symbols. I'm just seeing a bunch of numbers. And if you're doing that, you're really not thinking about the physics. You're just putting numbers into formulas. Okay. If you're pretty sure you aren't doing that, go ahead and keep it up, but watch it, because if units are wrong, it's penalized. Okay. I saw meters per second divided by seconds, came out meters per second. No, it doesn't come out meters per second. It comes out meters per second squared. And if you write meters per second, you're not noticing that it's an acceleration. Okay? Just talking about the style, what you do, the problems, and what you learn by doing them, because that's what you're going to have to rely on when it comes time for a test. Okay, we did have a question, and it's a blameless question. It says that negative 0.05 centimeters, is that from the top of the ramp to the bottom? I said, well, yeah, that's what I said. Okay, but nobody got that far. I saw that people weren't setting up a projectile problem correctly and just stopped you there. But hopefully this clarifies a way of doing it. Write down what you're given, write down the X, write down the Y in one form or another, and organize it in a way that makes sense to you. It could be better organized than what I did here, but I just got the information. Okay, I'm not going to dictate, write this, write that, write the other thing. Write down your information and draw your conclusions, not from equations you memorize, like got a square root in it. Okay. If I'd have done the calculations without the square root, I would have caught the fact that I'm getting seconds squared out of that, not seconds. What did I do wrong? Well, I was just careless and wrote the thing down. But you know, some people were writing down this equation without talking about where it came from. It's very easy to write down, this is the equation. And if delta y is, if v naught y is 0, then you get this equation, which gives you this solution. If you're just writing down this equation, you're not seeing that. You're not seeing the connection. Or maybe you are, maybe you're doing it in your head. Okay. And if you know it well enough to do it in your head, okay. But when you're doing on a test, maybe you're going to do that. But when you're doing homework, write it out. If you're not writing it out, you're not reinforcing it. And if you don't reinforce it, it might not be there when you need it. Or you might pull out an equation like this that doesn't apply because V naught wasn't 0. I say that all the time. You can memorize equations, grab this one in a situation where it's meaningless. Okay. It's only meaningful if V naught y is 0. There are special conditions on many of these equations that you pull out of your book or out of wherever, off the internet, whatever. Okay. If you don't see the connection, starting with the definition of average velocity and integrating acceleration, etc. Okay. You got to be able to go back to those fundamentals or to that V versus T trapezoid that we talked about a month ago. Okay. So I had the question that only works because V naught is 0. Yeah. And I'm saying that's a pretty valid assumption at the level of the ramp. At this small slope. Slopes are basically less than about 0.1. We can kind of get away with it unless we're making really, really precise measurements. Okay. And right now the measurements are not precise enough to justify worrying about that angle. And as I said, when we get to steep angles, it is important. We even can use analysis of the ball rolling down the ramp and the results to detect when the ball starts slipping instead of rolling in contact. Okay. And we'll talk about what that means, but that's coming up. Okay, so anyhow, this is pretty consistent with this. When I say pretty consistent, well, it's twice as much as this, but there are reasons why it's going to turn out that that's not much different than the results you're probably going to get when you analyze the experiment. All right. So then what's the net force in the ball while rolling down the track? if we know the PE loss from top to end, and we get the net force on the ball? Well, that's a little trickier. We can analyze the net force on the ball, not in terms of these results, but in terms of the slope of the ramp or the acceleration, okay? If the ball rolled from the top of the ramp to the bottom and attained a velocity of 0.7 meters per second, then we can use what some of you were starting to use. Okay, it started from rest, we can double the average velocity, or we can take, well, we got the final velocity, okay? The average velocity is going to be 0.35 meters per second, which means it takes about 2.5 seconds, okay, 2.6 seconds to go 90 centimeters. And from that, we can calculate the acceleration, because if it's like 2.5 seconds, then the acceleration is like 2.8 centimeters per second squared. Well, I'm losing my units here. Okay, 90 centimeters, and an average of 35 centimeters per second. Takes about 2.5 seconds. And the final is 70 centimeters per second. Divide that by 2.5 seconds, you get 28 centimeters per second squared. Okay, you get a velocity, and you can do that. Okay. If we get the acceleration, we multiply that by the 60-gram mass, we get the net force. Well, let's just talk about how to get the net force from the mass of the ball and the slope, because that's more relevant to the chapter we're working on. So here we have ball on the ramp. We do a free body diagram. Here's a ball. Here's mg. Here's the ramp. I'm exaggerating the slope. This is already exaggerated. I think this is a little steeper than that, but treat this as a schematic. And for the reasons I talked about in class, the fact that the acceleration is in this direction along the ramp, we're going to set up a coordinate system where the y-axis is perpendicular to the ramp. The x-axis is along the ramp. Now, you can calculate theta. Okay. The slope is 5/90, which is 1/18, meaning that angle is 1/18 of a radian, which is a little over 3 degrees. Your trigonometry should be up to figuring that out rather quickly. You should be very familiar with radian. 2 pi radians is the same as 360 degrees, so you can determine that a radian is about 57.3 degrees, I believe. And there's much more. Anyhow, we set up the x and y axes like this. Here's theta. I'm going to say that about 5 centimeters divided by 90 centimeters, which is about 0.044045. Okay. And the cosine of theta pretty darn close to 1, because by the time you square that, you get a 0.02. And actually, that's going to then be very close to 0.99. So if you want 0.99, okay. And if you want to be a little sloppy, if your experimental data isn't all that accurate, isn't all that refined, okay? And your experimental accuracy is pretty good on the experiment you did. If it's not all that refined, you can just assume that's one, which is essentially what we're doing, assuming your horizontal velocity of the projectile starts out, but your velocity of the projectile is initially horizontal. Okay, it's kind of equivalent, assuming that this is one and this is negligible. Okay, well, the thing is now we got angle theta here. So we draw the picture of the components and we label them. I'm going to draw the components in a different color. That blue should have stopped right there. There's mg y component. And my parenthesis kind of hit my G, but mg x component. There's your picture. And then you're going to have spin my y-axis a little bit. Your normal force here. There's no acceleration in the y direction. So the net force in the y direction is zero. So these add up to zero. So this is equal in magnitude to this. Okay. Now there's another force. Which is usually at little f. It's a force of friction. Got a little subscript there, kind of abbreviates friction badly. Okay. We're going to ignore that for right now. But it turns out rolling friction is very low between steel and steel. But there's also static friction. And that's a little bit subtle. We'll talk about that later. And that's going to make about a 30% difference in your acceleration. Not going to explain why right now. Okay. And what happens though is due to static friction, the ball rolls, the ball spins. If there wasn't any static friction, the ball would just slide down. Well, I'm explaining it. Okay, well, so be it. You want to store this away. Think about the system. Okay. When the ball's rolling, every particle in that ball has a velocity, a speed. So it has a kinetic energy. So the ball has a kinetic energy. It's about 30% of the total energy that it gets from the potential energy loss. Okay. Spinning ball has energy, just like the rotating beam has energy. I've asked you to calculate the kinetic energy of magnets on the beam. Well, every particle in that beam has energy. If you could integrate the kinetic energy over all the particles, which we'll do eventually, in about a month. It's not a difficult animal. But if you can integrate all the kinetic energies of all the particles, you develop formulas you can use to find the kinetic energy if you know the angular velocity. Okay, we're going to do experiments and draw that out over the next week. Okay. Anyhow, there's your situation. And if you analyze this and ignore the force of friction, you see mgx is mg sine theta. Mg is 0.06 kilograms times 9.8 meters per second squared times 0.045 is close enough. Okay, well, that gives you about 0.6, and 0.6 times 0.045 is about 0.27. And I did that quickly in my head, so you want to definitely check it. But that checks out. If that was a half, that'd be 0.03, and you multiply 0.03 by 9, you get 30, or you get 0.3, I'm sorry. Okay. And that's 90% of the 30, because 45 is 90% of 50, and 90% of 30 is 0.227. So that's what you get. Okay. And you need to think that through, work it out. 0.27 newtons. Okay. Now, how much work does that 0.27 newtons do on the ball? Let's just discuss it. I'm not going to work it out. I've got to do other things. Okay, I got a pretty good answer. And I kind of liked the way the answer was. I said, well, work is in kilogram meters squared per second squared. So wouldn't you multiply this force, which is in kilogram meters per second squared, by the distance, which is in meters, to get kilogram meters squared per second squared, which is the work? Yeah, it's a little easier to remember that work is force times displacement. Okay, but that's coming up in the next chapter. We talked about it a month ago, and y'all used it. And everybody did well on that homework. But it's been a while, so as I said, you ought to maybe review that. Just review that little problem set I gave you from the second day. Because there's a lot of content too that puts the chapters that we're studying into perspective. Make sense? Okay. Interrupt. Adam's out there. I owe him an HDMI cable. I was just going to hand it to him. They're discussing something important, so not going to interrupt them. Okay, anyhow. So the work. And if you write this, check out your units. Newtons times meters does give you joules. It also gives you kilogram meters per second times meters per second squared, kilogram meters per second squared times meters, which is kilogram meters squared per second squared, which is joules. You do a lot of reasoning. You did there off camera that I mentioned. You gain a lot of insight. You got to be careful because, for example, the calculation for work is exactly the same, has the same units as the calculation for torque, which is what accelerates rotating systems. And that's not joules. That's, and we call that meter newtons instead of Newton meters. I say Newton meters. So you know you're talking about torque. But the units are identical, and if you mistake that calculation of torque for work, whatever you're trying to design as an engineer is going to blow up. You're going to get in big trouble. People are going to decide you're not competent, okay? Or people are going to decide you make really bonehead errors sometimes and better not trust you. So then they make a manager out of you. Okay. I actually think that sometimes happens, but I don't know. I'm not in that field. All right, did you get the idea? You get what this problem is encompassing and what that math encompasses when we get done analyzing it? And I'm going to ask you to do kinetic energy and potential energy calculations. So here's the reason for doing all this. Because I think you can learn a lot by doing it and thinking about it. Okay, well, let me pause for a minute. I'm going to say this. Okay, theta would be the arctangent would be over A, and that's very straightforward to me, obvious triangle. And then I'm going to say plus, I'll say 180 degrees if A is less than zero. If A is less than zero, you know, the arctangent of B over A could indicate this angle, but it could also indicate this angle, right? And the conditions of the problem will tell you one of those solutions is usually absurd. It just ain't going to be in the third quadrant, or it just isn't going to be in the first quadrant, right? The arctangent's not going to tell you, but if you use this, it does. Because if A is less than zero, that means you're over here. Now that my labeling isn't right there. But anyhow, I think you get the idea. If A is negative, you're on this side of the x-axis. So you've got to be in the third quadrant. And of course, the arctangent could be in the fourth quadrant, but that could also indicate if A is less than zero, that you're in the second quadrant. If the arctangent is negative, that means your angle's either in the fourth or the second. If it's positive, it's either in the first or the third. Okay? This definition of theta takes care of that. So I kind of recommend it. And then, of course, the Pythagorean theorem, the magnitude squared of A squared plus B squared. I haven't seen anybody make a mistake on that yet. Someday I probably will. But get the idea. Okay. The problem of the astronaut given a push, okay, if she pushes off of the walls of the spacecraft is going to be accelerated in the direction of her push, and she's going to be accelerated in the opposite direction. Newton's third law, the force she exerts on the spacecraft is equal and opposite to the force the spacecraft exerts on her. So how can you get around that? Well, what you do is one of various things, but you could give her a medicine ball, let her throw it, see what her acceleration is, if the medicine ball's acceleration is, okay? And then maybe you have both of them positioned so they hit the walls of the spacecraft at the same time. Well, there's a question now, there's momentum conservation versus energy conservation. Would that have a net effect on the spacecraft? Well, we're not in a position to discuss that problem right now. Okay, but that's one idea you could go with. I mean, eventually Madison's ball going to hit the spacecraft, she's going to hit it. Whether she hits it or just, you know, brings herself to rest by grabbing something, whatever she grabs is eventually going to interact with the spacecraft, right? So you think about that, a lot of you said, oh, adjust the thrusters. At least two people said that, and not necessarily in so many words. But you know, there's good engineering thinking. Okay, but the physics thinking is much simpler if you just have her push off of something that it isn't attached to the spacecraft. Okay. let's go back to the ball on the ramp. And actually work one out. So we got a ball of mass M. So we have mg acting downward. Put an x and a y axis on this. And we automatically, at this point, want to project this vector on both axes. Okay. And you know, I thought about this when I did this last picture, wherever it is. Something I did earlier. So I can talk about it here. Just take a second. I said mgx is 0.027 newtons. X is in this direction. mgx would have been negative 0.027 newtons, wouldn't it? That makes sense? I mean, the vector is in this direction. Positive direction is that way. It's negative. And so is the 90 centimeters. Okay? 90 centimeters, the displacement vector is from here to here. So that should have been negative 0.027 times negative 0.9 meters. Still comes out 0.024 joules. When the force and the displacement are in the same direction, you do positive, the force does positive work. Imagine pushing a car. You're exerting force in the direction of motion. Now imagine realizing you pushed it too fast and there's a cliff up there and you get around the other side and you start pushing against the direction of motion. Then you're doing negative work and you're reducing its kinetic energy and hopefully get out of the way before it goes off the cliff. Or best case scenario, you stop the thing by doing something other than falling under the wheels. Okay. Well, anyhow, that's an important distinction. That was kind of a bonehead error of mine. And we'd actually put the negative sign here and here in the calculation. Okay. Now, going on with the idea. Got an angle theta here. And now, one way or another, there's another force acting on this. There's some applied force that's acting down here. Maybe it's something pushing on it from above. Kind of hard to imagine how a person could be standing here pushing in this direction on a ball on that ramp. So that's probably not what the force is. Okay. Matter of fact, practically, I don't think the force would be in that direction, but still something you can analyze. So that applied force has components. If you know, I've got to mark an angle. Let's say that angle is phi. You familiar with the phi symbol? It's the second Greek letter in the famous fee, fi, fo, fum. Okay. And unfortunately, some people pronounce this fee, which offends me, but it's common. I've seen friends from different universities who I like and respect because they're smarter than I am, use fee. I don't understand. But there it is. Okay, that's phi. Now that's going to be the angle with the y-axis. So your forces force components are negative mg sine theta and negative mg cosine theta. And then you have F applied sine phi and F applied cosine phi. Now let's say, instead of thinking about a ball, we think about a block sliding along the incline. Say anything about the block. We also have the normal force. And my big point here is that you don't know yet what the normal force is. And you might even have friction. So now we have a frictional force. Okay, so normal force is here. Applied force is here. Weight is here. And friction is here. And I've just written weight. That's what these components are. Applied force, here are the components. And normal force is purely in the y direction. And friction is here. Now, if you know the angles and everything else, and know how to calculate the force of friction, well, let's go over to the y components. You have equilibrium. Sum of all these forces is 0. If you're given M and theta and the magnitude of the applied force, you just write out whatever the number is for this, whatever the number for this is, and just F norm for this, add them up, you get 0, and then solve for F norm. Now, you've already seen that in some of the problems you did for today. Some of you already done some of the problems for Friday. Okay. Once you find the normal force, the frictional force is equal to mu times F norm, where mu is called the coefficient of friction. I'm not sure that's in the chapter, but I think it is. Just about has to. Okay. But if it isn't, I just want you to relate it to the lab situation. Okay. Now, we're out of time. And you take that for what it's worth. If you got a question on it, let me know. I can go into more detail. Okay.